In basic NLP, I had planned 5 theory lectures. So today is the last lecture in that series, and after that we'll be left with two more lectures. One more theory lecture, that is on transformer and BERT. So that is kind of advanced NLP, you can say. But in basics, I had planned only 5 lectures. So today is for fifth lecture. After this, we'll have a couple of lectures on hands-on. One hands-on will be on regex regular expressions, and a couple of more hands-on may be there. But theory is only one. So theory lecture is only one, which is planned. So this is last. After this, there is one more theory lecture. That's what I want to say. So after this, as I said, only one theory lecture. So let us proceed. So today's lecture is all about vectorization of words. So, can you see recording being done, Udesh?
Yes, sir. Recording started.
Okay, good, nice. So today lecture is all about converting word into vectors. So what we call the word vector as word embeddings. So I think we are already aware about a couple of techniques. So we have seen occurrence matrix, co-occurrence matrix, and then we have seen count vectorizer. Just count the word and replace that particular word by its count in the corpus. So this kind of couple of kind of vectorizer we have already seen. But the problem with these vectorizers is that the number of columns become very heavy. Like maybe in millions, number of columns can go in millions. So it becomes unmanageable even for normal computers to manage this kind of word matrix. So rows can be number of sentences in the your corpus, and number of words can be equal to big of words. So it can go in millions. So, and most of the another challenge is most of the entries in this kind of matrices are zero, because in a sentence, suppose big of word contain 1 million words. So in a sentence, hardly 10 sentence will be, in a sentence there will be 10 or 15 words. So out of that 1 million, in that row only 10 or 15 things will be one. One-hot encoding we do, right? So big of words is about 1 million words, and a sentence is containing 15 words. So out of those 1 million big of words, only 15 will be done one. So 15 will be one. So only 15 will be one, rest all entries will be zero. So it will be repeated for all the sentences. So most of the entries in these elements using count vectorizer or using say co-occurrence matrix and this kind of techniques. So a lot of entries are zero. So this kind of matrices, we know they are called sparse matrices. So we need to do some kind of techniques to handle them actually, because zero, if it is most of the entries, if they are zero, then we are wasting our space, right? Valuable computer memory space. So these are the topics. Have a look. I will not read them as it is, but have a look, and these are the topics we will cover. So as you can see, there is step 4 here on the right hand side box, which is disclosure integration. Step 5 is pragmatic analysis. So we'll finish our semantic analysis today and look into what is disclosure integration and what is pragmatic analysis. So we'll touch upon these two topics. Then we'll see what is rule-based and statistical NLP. So whatever we are doing so far, you say word entity, so like POS tagging or named entity recognition. So you saw that we trained our own model to, if you were to include new entities or we were to include new POS tags, so we need to train our own model. So we do some kind of training. So they are all statistical based approaches. So Spacey and all that. So these are all statistical based approaches actually. Even word to vec, whatever we have seen, is statistics based approaches. But there is another approach to NLP which is called rule based, and it is very common in Sanskrit scholars, like in universities which are teaching Sanskrit, because Sanskrit, Panini grammar is there. Panini, you might have heard. He was a old language scientist, very very old, so maybe 4,000 year old. He was scientist, so he is one of the very famous language scientists. So he has designed a language grammar for Sanskrit. And now modern scholars are wondering that how this gentleman could do this around 5,000 year back, how he could do it without computers, how he could devise grammar of Sanskrit without computers. So these guys are wondering still. So that his name is Panini. So this Sanskrit is a highly structured language and it is rule based. So like rule based language. So many scholars who are great at Sanskrit, they say that rule-based approach is much better than statistical approach, because in statistical approach you need lot of data to train your model. But in rule-based approach, nothing like that. Rules are there to form the sentence, and according to the rule you can work. And so there are many languages, old Indian languages like Pali. So they have devised Pali to convert Pali into English. They go through Sanskrit. So they convert Pali into Sanskrit first, and Sanskrit is a very structured language. So they use the rules of Sanskrit to convert it into Pali. So Pali to Sanskrit first, and then Sanskrit to English. Like that they go. So there are rule-based approaches, and they very much favor rule-based approaches to NLP. They said statistical approaches are not that great because lot of data is required to train your statistical model. So there are two schools of thought in NLP. One is rule-based, advocates rule-based, and one advocates statistical based. So whatever we have studied in our course, 100% statistical based, machine learning based. So it was a statistical approach. Okay, so now we move ahead. And we know, I think you are already aware what are word embeddings. So word embeddings are a compressed or low dimension version of mammoth size occurrence and co-occurrence matrices. So in last class we saw what is the co-occurrence matrix and what is the occurrence matrix. If you are not familiar, I think you need to see the video or you need to see the PPT. So you can revise that. So occurrence, co-occurrence matrix, whatever we saw, was all tricks to convert word into embeddings. Embedding means convert word into numeric vectors. So that's why we do all co-occurrence matrix, occurrence matrix. But they are very sparse matrices, as we discussed. So but word embeddings are usually compressed and low dimension version of these sparse occurrence and co-occurrence matrices. So we first form occurrence and co-occurrence matrices, and then we form some statistical technique like singular value decomposition. So singular value decomposition, you need to see in the web. We have not covered it in any of our classes. So singular value decomposition is a technique to convert high dimensional data to low dimension data. So we apply singular value decomposition on occurrence matrix and co-occurrence matrix and convert these parts at matrices into say shorts. These parts matrices we convert into dense matrices. All zeros get removed and only the entries we keep only entries which are having values. Okay, so this kind of numeric representation is called word embeddings. So now one of the word embeddings we saw was word to vec. So word to vec was having much shorter representation, say maybe 100 columns or 200 columns or 300 columns, maybe 1000 columns. That's all. So 1000 columns is very less in NLP terms. So word to vec, what we saw was generally we use it up to 300 columns. So it is much lesser than compared to our these number of columns are very much lesser than compared to our occurrence and co-occurrence matrices. Okay. So these are the specialities of this word2vec and glow, that modern word embeddings. So in the word embedding matrix, most entries are zero, and they still retain they still get to retain most of the information that a full size sparse matrix would hold. Like co-occurrence and occurrence matrix you form, they are very sparse. And word embeddings, as we say, they are compressed and low dimension version, but they still return all the information which is there in that bigger mammoth size sparse matrix. So I take a minute break here, and whatever we have discussed so far, if anybody has any questions, they can come forward. So any question, Dr. Shailesh, so far? Dr. Shailesh?
No, sir.
Okay. So now that word embeddings, we go ahead with word embeddings. And we see that there are two type of approaches to convert word into vectors. So word embeddings are nothing but word vectors, numeric representation of words. That's what we know. So there are two approaches. So one is occurrence co-occurrence matrix, and there is one more new approach we'll discuss of converting, which is TF-IDF approach. So something new that we'll discuss in today's lecture. One is TF-IDF approach, that is frequency based. So they count the frequency of occurrence of the word, occurrence frequency they count. And another is prediction based, like which are word2vec. So word2vec is prediction based, and we derive word2vec once we derive the word vectors by using shallow neural network. So this also will cover today, how word vectors are, how word2vec vectors are derived. So there are two approaches to it. One is CBOW, one is called CBOW, and another approach is called skip-gram approach. So they are used to convert word into vectors, and so that is called word2vec. So, and another is frequency-based approach. So frequency-based, couple of we have already seen, like occurrence matrix, co-occurrence matrix. So those we have already seen, and we'll discuss one more today, TF-IDF. So TF-IDF is more frequently used compared to occurrence and co-occurrence matrix. So that will, and then once we say derive our TF-IDF matrix, so they are very sparse. Then we apply singular value decomposition to on this sparse matrix to reduce the dimensionality. But in case of prediction-based approach, we already the matrix is very compact. So maybe the number of rows may be more. Number of rows can be your number of sentences, equal to number of sentences in corpus. But number of columns will be only 300, 400, like that. So 300, 400 columns are, as I said, are very less in NLP as compared to other frequency-based approaches. So there are two approaches. One is frequency-based and one is prediction-based. Both we'll discuss in today's discussion. So now we come to something. Something called latent discriminant analysis, latent semantic analysis (LSA), latent semantic analysis. So what is latent semantic analysis? So something. We have a corpus, and each sentence is one row of our matrix. We form some very sparse TF-IDF we form some kind of TF-IDF matrix out of that, and then what we do that LSC is a technique which on which we will have one hands-on. Suppose you are given a lot of corpus of documents, a lot big corpus of document is given. Suppose in that you have 300 documents. So in this 300 documents, you want to cluster together. Which documents are closer together, means which documents belong to the same topic. So that you will cluster together. So maybe 4 or 5 clusters are there in 300 documents. There are, for example, there are 5 topics. In 300 topics, there are 5 topics. But you don't know which documents belong to which topic. So you can use this latent semantic analysis technique to find the approximate topic of every document, and then club document with similar topics together. So what it analyzes, so I'll read out. So read with me the PPT. You can read with me. LSA analyzes relationships between a set of documents and the terms contained within. Okay, so whatever terms are there, see, document is consistent of terms or words, right? Different terms are there in a document. So LSA, like latent semantic analysis, is what it does. It analyzes the relationship between a set of documents and the terms contained within. Okay. So based on the terms, so they have whatever based on their topic, you want to group together. That's what is the aim behind doing latent semantic analysis. It uses singular value decomposition to scan unstructured data to find hidden relationships between terms and concepts. So basically, it uses singular value decomposition to see data is unstructured data, right? So any document is unstructured data. So to find the relationship between various terms and concepts which are hidden in the unstructured data, it utilizes a single value decomposition. Okay. So in LSA, we try to deduce the hidden topics represented by a text in the text. So to be very straightforward, what we do in LSA, we try to deduce the hidden topics represented by the text. So you are given a big text, but you don't know what is this topic, what to talk, what is the title of that particular, what title can be given to this particular text. So we deduce these hidden topics. So maybe LSA will suggest 4 or 5 topics, relevant topics. So you can choose based on that, like which topics, which this document belongs to what topic. So basically, LSA, very nice definition. In LSA, we try to deduce the hidden topics represented by the text. So we try to deduce hidden topics represented by the text. That's what is the aim of LSA. Okay. These hidden topics then are used for clustering of similar documents together. Yeah, we have discussed this. So once we have the topics of all the documents, so we can cluster with cluster similar topic documents. We can cluster. So maybe we have a set of 300, 400 documents. We have 5 or 6 clusters will be formed. So all cluster will contain document of similar topics. LSA is an unsupervised algorithm. Yeah, LSA is an unsupervised algorithm. Yeah, it's obvious, no? Because you don't have training data for LSA. So you are just given unstructured documents, and you have to find out you have to do clustering based on similar topics. So it is an unsupervised technique. So LSA is latent semantic analysis. We find, in short, try to find out topic of a document using LSA. LSA uses single value decomposition statistical technique, and then LSA is an unsupervised algorithm. So these are the highlights of LSA. Then suppose then let us come to this. See this. Try to read this document with me. The LSA returns concepts instead of topics. So we are doing one modification here. LSA returns concepts instead of topics, which represents topics which represent the given document. LSA returns concepts instead of topics, which represent the given document. It represents the given document. So we are not trying to say it returns concept instead of topic. So now in the next line, I'm defining what we mean by concept. So the concepts are list of words. Concept are list of words which represent the document in a best possible way. So concept are nothing but a list of words which represent the document in a best possible way. Okay, so this is the definition of concept. So suppose we have a data set. Suppose we have two documents. Two documents are there. And our latent semantic analysis, LSA analysis, gives that first document are having concepts of ball, shoes. See the first box on the left hand side. So first document, analyzing first document by LSA, we find that it has concepts of ball, shoes, goal, and win. So these are the main concepts of this document. Second document, second concept is ball, bat, score, and empire. So, what is your guess of concept 1 and concept 2? What can be topic for concept 1 and concept 2? So, concept 1, ball, shoes, goals, and win. So, these kind of thing more closely relation with football. They are more closely related with football. Then ball, bat, score, and umpire. So, they are more closely related with cricket or maybe say baseball. So if you are talking in India, in the context of India, so it is not baseball, it is cricket. Ball, bat, score, and empire. So this represents cricket. And concept one more closely represent football. So what our LSA analysis will give us? So LSA analysis will give us concept. That concept one is bat, ball, shoes, goals, and wins. This kind of set of sentences it will give. And then another concept is for another document can be ball, bat, another set of document. Concept is ball, bat, score, and umpire. So like that, it will give concept to you. Like it will not give a concrete topic name to you. LSA analysis will give concepts, and based on that, you can, if you want, you can deduce the concrete topic. So as I said, first concept belongs to cricket, football, so you can title that document as football, or second is more resembles with cricket. So you can say some related with cricket. So that's how what is. So we'll do one hands-on on this particular topic model. So it is called topic modeling. So we'll do hands-on on this particular technique. So as you are aware, as usual, your single value decomposition will work in the background and all work will be done by computer. So you just have to call the relevant method and it will do all the job in the background. But you should be aware that if we are doing topic modeling, we are applying singular value decomposition. So I have given the example of what kind of results you can expect out of topic modeling. So topic modeling will give you concept one and concept two. So these are set of words they will give as concepts. So any question till here? Dr. Shailesh, Sahu?
No, sir.
Dr. Shailesh, Uddesh, and Soman, and this Himanshu, any questions till here? Very simple, we have discussed.
Simple.
Okay, then we go ahead.
SVD, I am not able to recollect
what is that? What is that you are not able to?
This SVD, no, actually.
SVD, see, SVD I have not covered and I am not teaching it. So if you are interested,
what is the basic? What does it do? Because just
no,
you done it, but not able to.
Very big dimension. Suppose there are one dimension, 1 million by 10,000 matrix size is 1 million by 10,000. So there are 1 million. Sorry, 10,000 by 1 million. So there are 10,000 rows. One row representing one sentence, and there are 1 million. 1 million columns. So each column represents one word, big of word. So like that, suppose sparse matrix you have. So to reduce the dimensionality is very huge, not to analysis, for analysis. So if you want to reduce the dimensionality, we use SVD, single value decomposition. So that I'm not covering in this lecture, but if you are interested, you can always search in the internet and find out and train yourself to find out what is SVD. So I'll request
that upper triangular matrix and lower triangular matrix.
Yeah, something like that. So you need to search on the web. Yeah, so you have to search on the web what is SVD statistical technique. So if you just if you put SVD, you will get hundreds of articles on that.
Recollect now. It's a very that upper triangular matrix FEA. It is very commonly used.
Yeah. Even in FEA, it is used in mechanical engineering. So this is what topic modeling. We'll have one hands-on class in topic modeling. So maybe tomorrow's class will be on topic modeling, which I will take. And then we come to one more technique of converting your word into numeric form. Suppose you have a word matrix representation. So once you have done tokenization, so you have word, right? So each sentence you have tokens. So maybe one sentence is having 15 tokens, another is having 20 tokens. Like that, you have a matrix. So to convert them into a numeric vector. So why we convert into numeric vector? Because our very simple. Because our Machine learning algorithm will not accept word tokens. It always need numeric tokens. So you have to convert word into numerics. So that is the simple reason that we always thrive for converting any word token into numeric token. So this is one of the technique, TF-IDF, very simple technique. So first I will tell you the definition. What is term? So term is it is nothing but term frequency. It is called term frequency. So it is very simple. You don't go on the complexity of the equation which is there on the right hand side. I just put it for completeness. So simple. It is term frequency is very simple. Suppose you have 5 documents. So denominator it will come 5 because you have 5 documents. So each sentence you can say is a document if you want to define your document. Each sentence if you want to define a document. So you have 5 documents, so 5 will come in the denominator. Then what will come in the numerator? It is a ratio. Term frequency is a ratio. So term frequency is so denominator will be number of documents. What will come in the numerator? So for every document, we'll see for every word. So it will be term frequency will be for every word actually. So suppose there is a word called review. In first document, suppose review is repeating 2 times. So numerator will be 2. So we find the occurrence frequency of a word in a document and divide the total number of documents. Understood? Occurrence frequency of any word in a particular document divided by the total number of document. And term frequency is defined for every word in your tokenization. So it increases as number of occurrences of that word within document increases. So suppose occurrence frequency is more. So automatically TF will increase. So that is what is the definition of term frequency. Okay, TF. Dr. Shailesh, any challenge here? Very simple. Term frequency first of
Yeah, it is simple.
Yeah, so term frequency first of all is defined for every sentence in your corpus. Every token, for every token you have to define term frequency. Definition is, suppose you have 5 documents, numerator will be 5, and then we'll go word token wise and document wise. So suppose one word in that one particular document, if one word is getting repeated 2 times or 3 times, then your numerator will be either 2 or 3, and denominator will be constant always. It is the number of documents 5. So, and as numerator is what occurrence frequency of a word, right? So if occurrence frequency increases, term frequency increases. So what is the disadvantage of this? Can anybody tell me? Someone, can you tell me what is the disadvantage of this approach? Just guess something here.
Multiple words can have same frequency.
That is okay. We are okay with that. That doesn't matter, no? There is one very big disadvantage of this approach, so which I am explaining in the next slide. So what is the problem? See, so common words are there, like very common words like is, a, the, if you have not removed them, or some very common words which are not having much meaning, but they are occurring very frequently. So term frequencies will be more for them. So it will affect our analysis. Suppose even if you have removed the stop words and review in the sentence is occurring say 10 times. So and one review of what? So review of football game maybe. So review of a document or review of a legal document. So that is not coming. So that is coming only once. And review is coming 10 times in that document. So term frequency will be more because numerator is more. So that will affect our analysis, because if term frequency of something is more, so that will get more prominence. And more important, suppose what is review of legal document? So here legal document is more important word, but it is occurring only once. So its term frequency will be less compared to review, which is occurring 10 times. So we want more important document, more important word to be given more term frequency for our analysis. So that will not be achieved here, right? So that is the main advantage, main disadvantage of this term document frequency. So we then devise one more thing called IDF, inverse document frequency. So in next we discuss IDF. What is IDF? So IDF is nothing but it is called inverse document frequency, used to calculate the weight of rare words across the documents. Sometimes rare words are only important. We are talking is used to calculate the weight of rare words across the document. That's what we use for. So words that rarely occur in the document, the words that rarely occur in a corpus has a high IDF value. Words that rarely occur in the corpus have a high IDF score. Okay. So what is IDF? So IDF formula is IDF is represented by small w. It is equal to log of capital N upon DFT. So okay, let us see. N is what? So see in the right hand side. N is the total number of documents in the corpus. So in term frequency, total number of document was in denominator. So here total number of terms in IDF it is in numerator. And DFT. So DFT is what? Number of documents containing word W. So in TF, we were taking one document at a time. One document at a time. Here, see, numerator is very straightforward. Number of documents in the corpus. So suppose I have 5 documents, numerator will always be 5. What is the denominator? So suppose there is a word legal document. So legal document, I'll see all the 5 documents, how many times it is repeating. All the 5 in all the 5 documents, how many times it is repeating. So if it is repeating only once, then my document will be my denominator will be 1. So high value of IDF gives high value for a given word if it occurs often in one document and very rarely elsewhere. I'll repeat once again. IDF gives a high value for a given word if it occurs often in one document and very rarely anywhere else. So that's where we have. So if a term occurs in all the documents, occurs in all the documents, this IDF will be equal to 0. So we'll see a numerical example right now. So it will be more clear to Dr. Shailesh, any challenge with IDF? Anybody? Uddesh, IDF?
No.
Very
No, sir.
simple. Now you see a very nice. So now what we do? So TF we saw there is a challenge with TF. If word occur more frequently, more TF will be more. So we have divide IDF. So we combine them. Combine TF and IDF. We take always for every word, we take a product of TF and IDF to convert it into vector. So suppose you want to convert word into a vector. In TF IDF approach, one word TF IDF value will be product of TF and IDF. Okay. So if you see TF IDF, so if the more important word is in a document, for more important word, it will have higher TF IDF. So that's what we want. If word is more important, it should have more TF IDF. So if you take these kind of products, our scientist people have found that if word is more important, and if you take a product of TF into IDF, the product is more important. Sorry, word is more important. It's TF into IDF value, TF IDF value will be more. So now we see an example here. See here. Don't get carried away by because PPT is full. So don't worry, it is very simple. So first consider the right hand side, what I'm trying to tell. I have 2 sentences in my corpus, only 2 sentences. Sorry, 2 sentences, that means 2 documents. I'm considering each sentence as 1 document. So there are only 2 documents. Sentence 1, car is driven on the road. So Himanshu, there how many tokens are there in this? Don't remove stop words for now. How many tokens are there, including stop words?
7.
And how many, the second sentence is the car is driven on the road, and the second sentence is the truck is driven on the highway. So my second document is the truck is given on the highway. Uddesh, how many tokens are there in this? Don't remove stop words.
7.
7, right? So both documents are it's a coincidence that it's only a coincidence that both documents, sentence 1 and sentence 2 are having 7 words, 7 tokens. So each sentence, as I said, are separate document. Then we calculate TF IDF. Okay. So how you see that, how you calculate TF IDF? Now you come to the table here. Table here. So sentence 1 is represented by A and sentence B is represented by B. So document 1 is A, document document 2 is B. So that's how is the coding here. So now you see how the coding is, how the TF is done. So first of all, come to D, THED. So how the THED, TF will be calculated 1 upon 7. So can anybody explain me how it is 1 upon 7? How the TF of D in document 1 is 1 upon 7?
Number of occurrences upon the total number of tokens.
No. Number of occurrence in first document divided by total number of documents. So how many number of documents? 2 number of documents. So 2 number of TF is total number of words. That's how it is done. But in sentence we have defined something like that. Ratio of. Okay, so I think I defined it wrongly, little bit wrongly. When I defined TF, I am very sorry. When I defined in TF, I said numeric denominator will be total number of documents, but denominator will be total number of words in that document. Okay, so TF will be occurrence frequency of that word divided by total number of words in that document. So denominator will be total number of words in that document. Sorry, I defined wrongly. So TF will be numerator will be occurrence frequency divided by total number of words in that particular document. Okay, so that's what is TF. And in this IDF is the total number of documents in the corpus divided by the number of number of documents containing that word. So now if we come to this, so that's why doing numerical is very important, because if we do something, if you have a wrong concept, then if you do a numerical hands-on, so it will be very crystal clear. So as Himanshu said, for document A, the TF for D will be, because D is occurring only once, so numerator will be 1, and there are number of words are 7, so denominator will be 7. So similarly for B, D will be, D is occurring in document B, means sentence 2. D is occurring only once, and number of frequency is, number of words are 7, so 1 divided by 7. IDF. So what will be the IDF of D? See, now D is occurring in both the sentence 1 and sentence 2. So IDF is what? So again go to the definition of IDF. So IDF is total number of documents in the corpus. So there are 2 documents, 2. IDF will be 2. Document numerator will be 2, and denominator number of documents containing word W. So these are occurring in both the documents. So 2 upon 2. So 2 upon 2 is 1. So log of 1 is 0. So see, TF IDF value of D is 0, because it's a common word occurring in both the documents. So similarly, car is occurring in only document A. So 1 by 7 TF. And document B, it is not occurring. So its IDF will be 0, right? So 0 upon 7 will be 0. What will be its IDF? What will be its IDF? So number of documents are 2. And IDF. So numerator will be 2 divided by 1. So car is occurring in only one document. So 2 by 1. So 2 by 1 is 2. Log of 2 by 1. See, log of 2 is 0.3. So if you take 1 by 7 into, so if you do TF into IDF, the product if you do, that comes out to be 0.043. Similarly, truck is not occurring in A, so its TF will be 0. And IDF, so TF will be 1 by 7. For document B, the TF will be 1 by 7. And IDF will be, again, IDF is what? Number of documents. So number of document 2 divided by 1. So how many documents truck is occurring? Only 1. So 2 by 1, again 0.3. So product of 1.7, 1 by 7 into TF is 1 by 7, and IDF is 0.3, again 0.43. Similarly, if you calculate everything, road, you go to road. So road is occurring in road, TF will be road is there in only first sentence. So TF will be 1 by 7. So no, road is there in only first sentence. So 1 divided by number of words. So 1 by 7. Second sentence it is not occurring. So 0 divided by 7 is 0. IDF. So IDF will be road is occurring. So number of documents are 2. So document will numerical will be 2 and divided by the denominator because road is occurring in only first sentence. So denominator is 1. So 2 by 1.3 it's IDF. So similarly highway. Can Udesh, can you explain TF IDF calculation of highway?
Yeah, highway doesn't occurs in sentence document A. That's why its TF is 0. Then for sentence B, it occurs only once, so 1 by 7 because there are 7 words in sentence B. Next up, we calculate IDF value, so it occurs only once across the 2 documents. So 2 by 1 and log of that value, so 0.3 approximates to 0.3, and we multiply these values means TF of sentence B with its IDF. So we get TF IDF value.
TF of sentence, no, it is wrong. TF of highway. We multiply TF of highway with IDF of highway. So
Yeah.
that is 1 by 7 into 0.3 is equal to 0.043. Okay, so got it. So now you see here, there are important words are car, truck, road and highway. So they are having an IDF value of 0.043. Rest, all common words are having ITF into IDF of 0. TF IDF product for all common words is 0. And important word here are car, truck, road and highway. So they are having a IDF of TF IDF product of 0.043. So now we see that TF IDF of common words was 0. So they are not significant in our matrix because truck is driven. So driven is in both the sentences. So its TF IDF is 0. So got it how these calculations are done? So all this will be done by one, just you have to call just method. All this will be done in the background by your friend computer. So that's how we do TF-IDF. So this is one of the techniques to convert document corpus into vectors. Okay. So this is one of the technique to convert into vectors. So now we get into, so we have this example. So this example I'll cover in the tomorrow's class. So topic modeling. So now we come to another approaches of converting word to vectors. That is, in other words to get how to get word embeddings. Word embeddings is nothing but word vectors, right? So there is one technique in which we use shallow neural network. Shallow neural network, if only one hidden layer. So there is one input layer, one hidden layer, one output layer. It's a shallow neural network. So that's what we use to derive our word embedding. So one approach is CBOW. So CBOW means continuous bag of words. Continuous bag of words means, see what happens. You see here in the neural network, input is what? Input is first sentence. So input is one sentence that you say context 1. Then you see another sentence as input vertical bar, another vertical bar you see on the right hand side, that is another input, that is context 2. So I am giving two contexts or context 1, context 2. So I am giving two contexts, and in between whatever the gap is there, that word I am trying to predict. Like I am trying to complete the sentence. I have fill in the blanks in a sentence and I am trying to complete the sentence. So first context is I am giving in the form of one odd vector. So it has only one word. First context 1 is having only one word, O. So it is represented by 1 and 4 zeros. Context 2 is having set. So it is having 2 zeros, 1 and 2 zeros. So these are the two one odd encoded vectors I am supplying as the neural network, and I want to find the target. Actual target is my second word 0 1 in the form of one odd target, one odd encoding. So 0 0 1 0 0 0 0 0. So 0 1 0 0 0. That's what I'm trying to predict. Okay. So I will give a more concrete example. So just I want to for in a cut short, I'm doing filling the blanks here. Like I have a blank word in the sentence. I have a complete sentence. In that one sentence is blank, and my neural network is trying to predict that particular blank sentence. In the blank, it is trying to fill up the proper word. So this is continuous bag of word approach. Just for now, stop it here. Next, it will be more clear to you, like how we use it and why it is used for. So next slides, it is more clear. So another, see, this is one approach. So fill in the blanks I am trying to do. I have a sentence, both the sides I have words, and in between one something is vacant. Fill in the blanks. So I am trying to fill that gap using trying to predict that word using a neural network. So now another word is reverse approach. In the fill in the blanks I have word, and right hand context I am context 1 and context 2 I want to predict. So see here, see I have a sentence here, the cat on the mat. The cat sat on the mat. So in CBOW approach, I had the cat space on the mat. So I wanted to predict set in CBOW approach, continuous bag of word approach. So I had the cat I had already with me, on the mat I had already with me, and set I wanted to predict. Now here it is reverse. I have set with me, SAT I have with me, and the cat I want to predict, and on the mat I want to predict. So both left hand side and on the right hand side, I am trying to find proper words. So I am having only set with me, and then I want to predict the cat and on the mat. So a more appropriate words to match set on the left and right I want to predict. So Uday Soman, can you tell which approach is more difficult?
So predicting the rest of the sentence using
Yeah, so that is called skip-gram model. So that is skip-gram model. So you can see that skip-gram model is exactly reverse of CBOW, continuous bag of words. So it is exactly reverse. Okay. So now we'll see how we utilize them. So skip-gram model, both skip-gram model and CBOW are approaches to generate word vectors. And once trained, the matrix between word matrix between input layer and hidden layer gives the word embeddings. Okay, so we see here. Suppose see here now. I have given an example. I tried to make I cooked up an example for you. So this is a simple neural network. Okay, so we have an input, we have a hidden layer, we have an output layer. Very shallow neural network. Only 3 layers: input, hidden, and output. So my input is the class are genius students. This class are genius students. My input is I got a document, which document is this class are genius students. So I removed stop words and all. So class, genius, and students. So these are my tokens out of this because I removed the stop words. This was a stop word, R was a stop word. So I removed them. Class, comma, genius, comma, students. So these are my tokens. Now in the neural network, what I'm giving, this is script-gram approach. So what I'm giving only genius. Genius I'm giving as input. So I'm giving in the form of word in the one-not vector. So 0, genius, 0 is that's what I want to supply to 0, genius. So 0, genius, see there are 3 words in your bag of word. There are only 3 words. So first is class, second is genius, and third is student. So it is 1, 1, 1. So 1 is class, 1 is genius, and 1 is student. So like that, positions. So now I'm supplying a word vector of only 3 elements because our bag of words is only 3 elements. So I'm keeping class as blank, so 0. I'm supplying only genius. So genius I'm supplying, and students I'm keeping as 0. So that is what I'm giving 0, 1, 0. Understood, Dr. Shailesh? Is this understood?
Yes.
So class genius and 0. So 0, 1, 0, this is the word vector I am supplying. And what I am expecting output as 101. So 101 is what? Class 0 and student. So class 0 and student, that's what is my prediction. Understood now? Because in a skip-gram model, I supplied the middle word and left and right words are supplied by the neural network. So class 0 and student, that's what I want my output. Okay, so now once I fully train this model with say 10,000 examples like this, if I train completely through the neural network and in which all the inputs were, all the input was same. So in that case, once my neural network fully trained, then the weight matrix between input layer and hidden layer will be my word embedding. Understood? I am trying to find out word vector for genius. So in a scriptgram model, once I fully trained my network, so the weights between neural network weights between input and hidden layer. So weights between input layer and hidden layer, they will be our word embeddings. So that's how we take our word embedding. So is this understood? Sauji, is that understood? Sauji, are you there? Someone, is that understood?
Yes, sir.
So word vector between input and hidden layer will be your word vector for genius. So that's how they have derived it. Understood? So Dr. Shailesh, is this understood?
Yeah.
The weight matrix between input and hidden layer. Once you first fully train your neural network, and once you are satisfied with output, the weight matrix between input and the hidden layer will be your word vector or word embedding for word genius. That's how we find out. Okay, so now you compare CBOW and skipgram. So very simple. Like in CBOW, you fill in the blanks for a word. But in skipgram, as we said, we do reverse. We have middle word and we then try to predict left hand sentence and right hand sentence. Okay. So that's what we try. And so this is just for a comparison given here. So now here, now after that, I think you are already aware. So here we have a very famous test for word vector. So what is word embedding? We'll say now word embedding, we know how they are calculated word embedding. So word embeddings are word vector representation. Word embeddings are word vector representation where words with similar meaning have similar representation. So King of England and King of Russia, both will have a similar representation. Little different will be there because they belong to different countries. But the cosine angle between them, the angle between them will be very small because both represent kings. Okay. Then word to vec is a large corpus of text as text input. Word to vec takes a large corpus of text as input and produces word vector space. Yeah, here, like that we have seen. So this was a word to vec approach. So it takes a large corpus for training, and once fully trained, then the weight matrix between input and hidden layer will be your word vector. So that's how it works. So see the representation of man and woman here in the vector. So man vector and woman vector, though they are different, but angle between them is not very large. Okay, then you see king and queen. So king and queen both belong to royal family. So angle between them is very small. But you see king minus man. So king minus man means king minus man is almost perpendicular to woman. So if you say king minus man plus woman, so it exactly represents your king. So king minus man plus woman, it exactly represents your king minus man plus woman. It should be queen, right? So it is done in the. So if you take the vector of king, take the vector of man, minus, just do a simple minus of king minus man, plus add a vector of woman to it, you will exactly get the vector of a queen. So even if you do this vector addition in a graphical space, as you do in physics or maths. So even if you do the same thing, so you will get exactly same vector. So it is that's how it is accurate. So Doctor is Sahuji, are you there? Sahuji,
I am there.
is it understood so far?
Uh-huh.
And this is understood. This how Scriptrum model calculates.
Mm-hmm.
It is understood, right?
Right.
Yeah, you didn't reply, so I was little concerned that you are there or not. So this is how what to back representation. So there are two main kind of representations here. One is globe. So globe is developed. Globe is another presentation which is developed by Stanford Research Group. Word to vec, how word to vec is developed, that I have already given. It is developed using shallow neural networks like this. Training a shallow neural network like this, it is developed word to vec, and your globe is developed. Is developed using globe is developed using that matrix factorization technique. So that's what we have learned now, a single value decomposition, TF, IDF. So those similar kind of techniques that Stanford group has used and done matrix factorization, and then they have developed the matrix globe. So globe is developed using matrix factorization techniques, which are we saw them, couple of them we saw them. Use Cockroach first make your TF-IDF matrix, and it is very sparse. So use single value decomposition to make it a dense matrix. So to reduce the dimension, you use SVD. You do that. So like that techniques they have used, and something like that they have used, and they have arrived at vectors for embeddings for words. But word to vec is different approach. They have done it using neural network, training shallow neural network. So, and why, which to use when, like these two are most popular, glow and word to vec, and both give usually like similar results. So these are very popular. I cannot say that word to vec is better or glow is better. So try with glow word to vec first, and if you are not happy, then come to glow or try with both and compare your results. So if you want to put into machine learning algorithm logistic regression, first try your logistic regression with word to vec approach. Then you have time, then you try with glow also. So you cannot say which one is better. And there is one more thing coming very quickly or very fast, which is coming up. That is another approach that is called fast text approach. Fast text. So many people are nowadays using fast text, and it is developed by Facebook AI research. So Google AI, and Facebook AI. So they are very prominent names in the world of AI research. So fast text is a technique of getting word embeddings or converting word to vectors. So this fast text technique is developed by Facebook AI. So advantage is there with fast AI is that it has word embeddings for 157 languages in the world. It has word embeddings including Hindi, Marathi, Goa, Malayalam, and Tamil. So these 5 Indian languages, and maybe there may be many more Indian languages. But what reference I got, in which only these 5 languages were written. So Hindi, Marathi, Goan, Malayalam, and Tamil. So these, and including that, 150 other languages, word vectors, word embeddings are already present. What does it mean? You provide the word, so FastTrack has ready vector for that. Just download the corpus. Like in one of my hands-on, you downloaded one Google corpus, right? Google.bin library, you could download it, right? So that was word to vec representation of every word. So that library you downloaded, right? Ready-made library, word to vec. So that was Google something.bin. That's what you downloaded from internet first, and then instantiated that into word to vec, right? So that's how fastest is having ready word vectors. You don't have to do anything. Just make your corpus, just make your tokenization, and just pass it with FastTag. It will, in 1 second, it will convert it into, without any effort, it will convert it into vector. Ready embeddings. And similarly, glow and word to wake also have word embeddings for English. That's what I know. If they have for others, I don't know. But for English, definitely word to wake and glow both have ready word embeddings for every word, almost every word. But in fast test, advantage is it is available for 157 languages. So see, mind it, you have ready word vectors available for every word in 157 languages, in which Hindi, Marathi, Goa and Malayalam and Tamil included. So you can do your analysis in your own Indian languages as well. So that is the advantage of fast test. So I have seen a couple of examples where people are using fast test. So this is another thing which is coming very fast. So then we have, then I want to remind you which are the steps. So till now, whatever we have done was semantic analysis. So we were at step 3. Semantic analysis is now very much finished. So we have done it in great detail, like semantic analysis. Now there are two things you might be wondering: what is disclosure integration and pragmatic analysis. So you might be wondering what these two are. So we'll touch upon them. We'll not go in very much detail into this, but we'll touch upon them, that what these are. So till now, any challenge? Anybody has any question?
I need to drop off. Maybe.
Yeah, you are almost done. So only 2 PPTs are left, so you can drop off. No problem.
Thank you all. Have a nice.
Yeah, thank you very
Okay,
much.
thank you.
So only 2 PPTs now. So disclosure integration. So what is disclosure integration? So till see lexical analysis, you can say breaking down into tokens and sentences. That is lexical analysis. Syntactic analysis ends with POS tagging. Semantic analysis, we do NER and then word representation, word embeddings, and all those things come into any semantic analysis. Then disclosure integration. So what is disclosure integration? That is step 4. So see this left-hand side box. There are 3 sentences written. Ram won the race. That is sentence 1. Mohan ate half of a pizza. Mohan ate half of a pizza. That is document 2. And third document is he liked it. Now can anybody tell me that he liked it, so he belongs to Mohan or Ram? Can you tell that? He belongs to Mohan or Ram? Sauji, can you guess what he likes it? When I say he likes it, it is in reference to above. He belongs to Mohan or Ram?
It should be Mohan, right? Recent last sentence only it is to
No, it is not correct. That is not correct. It can belong to Ram as well. So it is, ambiguity is here. Computer will get confused. Even humans get confused, so computer also will get confused that he belongs to either Mohan or Ram. So it is nothing. It is nothing that it belongs to the last sentence. It can belong to both. So there is a referential. This is called referential ambiguity. This kind of phenomena is called referential ambiguity. So referential ambiguity is the ambiguity that can arise when a reference to word cannot be determined. So here we wanted to find reference to word he, but we don't know whether it is Ram or Mohan. So this kind of ambiguity is called referential ambiguity. Okay. And when we try to resolve this referential ambiguity, so that is called disclosure integration. So goal of disclosure integration is to resolve the referential ambiguity. Done. The goal of disclosure integration is to resolve the referential ambiguity. And now you know what is referential ambiguity. So that is what is your disclosure integration. It is very important. Suppose you want to suppose if sentence was this: Ram killed the victim, and Mohan killed the Ram may have killed the victim, and Mohan may have killed the victim. Sentence is Ram may have killed the victim. Second sentence is Mohan may have killed the victim, and then I say he was punished. So who was punished? Ram was punished or Mohan was punished? So this is ambiguity, right? So that is called referential ambiguity. So we are trying to find reference to he. but the reference can be Ram or Mohan. So we have to resolve it. So when we try to resolve it, that particular science or that particular effort is called a disclosure integration. So this is also very important in finding proper meaning of a particular purpose, or when you analyze a sentence. So this kind of referential integrity might arise at many places. So you want to resolve it. So you want to resolve it. So this kind of things is called disclosure integration. So that is one more step, and I am not going beyond this step. And then next step 5 is pragmatic analysis. So pragmatic analysis is again, see, pragmatic analysis is see the left hand side box. There are 3 sentences. Average is 18, average is 18, average is 18. So in what context you are talking about? So context may be you are talking about a mathematical sequence whose average is 18, or you are talking about a vehicle in India whose mileage or average. Generally, mileage in colloquial language is called average. So mileage is 18, or you are talking about you are talking about a mathematical language. You are talking about something in mathematics where average is 18. So which context you are talking about? So when we are trying to resolve the context, to interpret the meaning of sentence, we need to know we need to understand the situation. Like, so in which sense we are telling the average is 18? We need to understand the situation around it, right? That's what we need to understand. So to tackle such problem, we use pragmatic analysis. So that is what is pragmatic analysis. So when we try to understand the context in which our sentences are written, so that we called as pragmatic analysis. And see, and here disclosure integration, we try to resolve the referential ambiguity. So these are the small differences, and so that's where I stop. And if I get more numerical examples on disclosure integration and pragmatic analysis, I try to share with you. But so far I have not done the research, but I want to do that research, that how to do, like in NLP techniques in terms of Python, how to do disclosure integration analysis and how to do pragmatic analysis. So these things I need to do research, which I will do maybe today evening or tomorrow morning. And if I get something, I will share those things. But we may not have proper classes on that. But definitely, I will share resources with you, like how disclosure integration is done and how pragmatic analysis and so on is done. So I'll share the resources with you. So I promise that, but I don't promise of taking classes on that actually, because already we are too much into it. So now again, our full NLP: lexical analysis, syntactic, semantic, disclosure integration, and pragmatic analysis. So now disclosure and pragmatism I have just touched upon, and then as I said, I'll share Python resources, how to do disclosure integration, how to do pragmatic analysis. I'll share with you. And but till semantic analysis we have done in great detail. And I think semantic analysis, word to vec, I think you are already using it, and I have already given one assignment to you. So I had planned one. Numerical here. So I had planned one numerical here. Here on complete. I had planned one complete hands-on Python hands-on using word to vec. So I think you are already doing this, so I need not cover this. So maybe I will cover this topic modeling tomorrow. LSA, topic modeling will be tomorrow's topic. That's what hands-on I will cover. And that's it. And then there are two, as I discussed in the beginning, there are two rule-based approaches to NLP. So I want you to read this. What is the difference? It should be in your knowledge, because in our mostly in your companies and in your day-to-day life, you will all time you will be using statistical NLP only. Statistical NLP approaches only you will be using. Nobody will use rule-based approach. But in some R&D cases, or maybe if you are doing some language research or those kind of things, rule-based approach may be more important for few people. But practically speaking, for professionals like us who are working in a corporate sector, mostly will be 90% of the cases they will be using statistical NLP. Like that's what we have discussed. So I will not read it out. Just I just keep it open for a minute for you. Just if you are interested, you can read out the differences. So the advantage of rule-based NLP is that it doesn't require large amount of data, but statistical approach, training of your neural network is required, right? So it requires large amount of data to train your and then rule-based approach requires more skilled developer, because you are keeping many complex rule to define your understand, to analyze your language text and all that. So you need very skilled developer there. And so rest you can, I think it's in front of you for a minute, so you can read it out. And so that's the end of our basic classes, 5 basic classes ends of it. And so if you ask where precision is higher, so precision is higher in rule-based NLP. But in the case of a complex language like so if Sanskrit is there, definitely rule-based language works. If Sanskrit is there, because it is fully defined by rules, very structured language. But in English, which is not that structured language, rule-based approach is not that great. So better go for statistical approach. Okay, so that's how it is. So I close here, and thank you very much for your attention, and I keep it open for questions for a minute if anybody has any questions. And as I said, I'll try to give some resources for you to study on disclosure integration and pragmatic analysis. So any questions here? So that's what pretty much basics of NLP. Next class we'll learn some advanced techniques, transformer and BERT. So BERT is a very in thing, because without BERT you cannot manage you cannot manage NLP analysis in corporate sector. So you must know what is BERT. So it is a similar technique to BERT to a kind of glow, better technique. It's a better technique which is based on transformer model. So this is transformer model. So see, it is very complex model. It is very complex. This is a neural network. So it is a very complex neural network, but will not get into detail of transformer, because that is another topic. But I will make you understand that BERT is a technique which is based on transformer model, and we'll try to understand why it may be better than what to wake and glow. So that's what we'll try to understand in our one of the lectures.